Good day, everyone. I am Remus Gem A, Rivera, and before formally starting this presentation about wallpaper groups, the hidden art of geometry, allow me first to show you a couple of pictures which may seem familiar to most of you. Take this time to recall if you have encountered at least one of these pictures at some point in your lives. A Christmas-themed gift wrapper, a wall of bricks, or even a honeycomb. These small aesthetic details make up a part of someone's occupation, day-to-day activities, and special occasions. If you will look closely, these objects are composed of repeating patterns, which creates a mesmerizing effect in its art. But have you ever wondered how these real-life patterns are formed? Has it ever come into your thoughts what elements are composing these patterns, and how do we classify them? We will be tackling them later, but first let us take a look at what we inspire you to learn throughout this presentation. First, we will aim to understand the foundational concepts of wallpaper groups. Second, we aim to classify wallpaper group patterns based on their properties. And finally, recognizing its significance and application in real-life events. Now we have a bulleted form for the flow of the presentation and what topics we will be discussing for this video. First, we will be discussing isometry and its types. We will be discussing the definition of symmetry, the symmetrical patterns, consequently, which will include rosette patterns and its types, frieze patterns and its types, and finally, we will be having a main discussion on wallpaper patterns, specifically a brief background on his history, the crystallographic notation, the 17 types of wallpaper groups, the wallpaper groups simulation website. Now let's start with isometry. Isometry is a mapping of a metric space onto another or onto itself so that the distance between any two points in the original space is the same as the distance between their images in the second space. In other words, this is used to describe the process of moving a geometric object from one place to another without changing its size or shape. After the object reaches its final position, the object remains unchanged or invariant in the plane, since isometries preserve relative distances between the points of an object. Just to make this into a clearer perspective, a transformation is defined as a process by which the points are shifted in the plane to possibly new locations in the plane. These are various ways for two-dimensional figures to move places around the plane, but only four types of isometries are possible, namely translation, rotation, reflection, and a glide reflection. These transformations are also known as the basic rigid motions. Let us start with translation as the first type of isometry. It is an isometry that moves every point in the plane at a fixed distance in a fixed direction. Take this square as an example. Within the plane, translations occur when objects are being slid around. If one point moves at a different position, the other points follow as well, meaning these points are fixed, since they end up in their positions before being translated in the first place. As you can see, we have an animation of a square where it being slid across a straight line. We can see that the points are remaining intact in their places on the object despite moving into a different place. This preserves the orientation of the image or the points and sides of the object, meaning these are stationary. Hence, this is considered as a proper isometry since the left side of the square stays left, the right side stays right, and so on and so forth. Now let's proceed to the next isometry type. We have rotation. A rotation involves an isometry that keeps one point fixed and moves all other points at a certain angle relative to the fixed point. In rotating an object in a plane, one point must remain fixed while the other points are the only ones being moved around, depending on the central point, also known as a fixed point. In understanding how rotation works, we should know the pivot point and the amount of rotation based on the angle and direction of the movement. As an example, here is a figure of a triangle being rotated 90 degrees counterclockwise on a straight line. Let's have a look at it again. This is also considered as a proper isometry, since the objects remain constant in their positions although they are being moved into another place in the plane. Next, we have reflection. A reflection in the plane moves an object into a new position that is a mirror image of the original position. Before understanding reflections, one should know the axis of reflection the object will move upon, which is illustrated using a line. Since this works similarly to a mirror, this is considered as an improper isometry, since the orientation, position of the points, and frame of reference changes in the reflected object as the left side can become right, clockwise motions can become counterclockwise, and vice versa. The only fixed points here lie on the axis of reflection while every point in the object changes places. Here's an animation to visualize. Let's see the semicircle being reflected along the straight line. Now let's proceed to the last type of isometry, glide reflections. A glide reflection consists of a translation followed by a reflection. The object's movement in the plane consists of an axis of reflection illustrated by a line, as well as where the parallel directions of the translation and reflection take place respectively. However, all of the points change upon reflecting after the translation. In this isometry, one must know the direction of the object's reflection and the positions where these points will end up in the plane. Hence, this is considered as an improper isometry. Let us take a look at this animation. We can see that the triangle is being translated and then reflected along the straight line. Now let's proceed to symmetry. Symmetry is defined as the balanced and proportionate similarity that is found in two halves of an object. This is where harmony and mesmerizing details take place. Now, allow me to ask you have you ever encountered or witnessed a butterfly in real life? In fact, a butterfly is a real-life example of a symmetry in nature. In a simpler sense, an object obtains symmetry if a mirror line can be drawn in the middle in order to show the precise proportion of both sides. If you will look closely at the image, the line of symmetry or the mirror line can be found in the butterfly's body. And at the center, we can see here, this is the mirror line. Next, we have the left and right wing as the proportional objects in terms of size, shape, color, and even appearance. Hence, it is considered that one of the characteristics of symmetrical objects rely on the identical features of both sides respectively. Now let's tackle the symmetrical patterns. First, we have a rosette pattern. Rosette patterns consist of taking a motif or element and rotating or reflecting it. It has been mentioned that understanding these is the first step in classifying all possible symmetry groups in the plane figures. When we say rosette patterns, we pertain to the rotational and reflectional symmetries which can be found in the plane. Let us dig deeper. Let us have the first type of rosette pattern. We have cyclic. It is denoted as Cn, and it has an n-fold rotational symmetry and no reflectional symmetry. As a real-life example, we have a pinwheel here. Since the spinners are considered the fixed points or the center points, where these symmetrical objects will rotate around it. The rotational objects here are considered the paper wings. Next, we have dihedral. This is denoted as the capital letter D. This has an n-fold rotational symmetry and a reflectional symmetry. As a real-life example, we have an image of a sunflower. We can see that the center of the flower is considered as the pistil, or the center points, which the symmetrical shapes or the petals will rotate around it. In the dihedral pattern, we can see here that the same concept is applied. However, the pattern is mirrored as it circulates around the center point. Here is a table which you can really pause this video to closely examine it to see the similarities and differences of the cyclic and dihedral types in 5 different steps. Now let's talk about freeze patterns. Freeze patterns are an infinite strip with a repeating pattern. Specifically, this is a lengthened and continuous strip of imprinted designs composing of repetitive motifs. In this pattern, each freeze group is symmetrical under the translation, which is denoted by the letter T in the direction of the strip. We mentioned that denoted as the letter T, since we will use the John Conway naming system for phase patterns. We use the letter T for translation, H for horizontal reflection, G for glide reflection, R for 180-degree rotation, and finally the letter V for a vertical reflection. We can see here the John Conway naming system, a visualization here, using the letters P and Q. For the translation, we have here letters P and Q being repeated 4 times, and the letter B and D in the bottom. This is being translated horizontally, going to the right. Next, we have a horizontal reflection. This line here is the mirror line, or the axis of reflection. And the letters here are being reflected, as you will notice. For this one, the same concept applies, but in a vertical manner. We can see this is the mirror line, and it is reflected. Here we have a rotation. The letters P, Q, and BD are being rotated at a 100-degree angle here. Next, we have a glide reflection. We can see here that this composes of a translation and a reflection. It satisfies both the letter T and the letter H. Now we have the combination of the T, the letter H, and the letter G. We can see that it satisfies the translations and the reflections evident here. Next, we will study the 7 types of phase patterns. We can see the naming systems here are used using the symmetry type, the IUC notation, and the Conway naming system. Let's start with the letter T as the symmetry group, the P111 notated by the IUC, and HOP using the Conway system. It has only a translational symmetry. We can see here that this foot is being translated 5 times in the plane horizontally. This is notated by the letter F under the Conway naming system. Here's a real-life example. We have a wavy translation here, as we can see in a mosaic border in Alcázar de los Reyes Cristianos, which can be found in Cordoba, Spain. Next, we have the TV, the PM11 or the silo. It has a vertical mirror symmetry spaced half the translation length. As a composition, we can see here that the foot faces one another, and it is being repeated along the plane. And it is notated using the letter T 5 times, using the Conway naming system. Here is a real-life example. Next, we have the letters TG, P1A1, and a step. It has a glide reflection half the length of the translation. Hence, it produces an alternating effect or a zigzag effect in a horizontal manner, since it is first translated and it is reflected here at the bottom, half of the translations being made. We denote this using the Conway naming system as the letters P and B. Here is a real-life example, the leaves of a Texas sugar berry tree, since we can see that in the leaves here, we can see that these are alternating left and right. Next, we have the TR, the P112 or the spinning hop. It has only a 180-degree rotation spaced at half the translation distance. We denote here the 5 letter ends based on the Conway naming system, and we can see that this is translated 5 times, and it is rotated at a clockwise angle. At a clockwise motion, at a 180-degree angle 5 times. Here's a real-life example. Next, we have the THG, the P1M1 or the jump. It has a horizontal mirror symmetry, denoted as 5 letter Ds based on the Conway naming system. It is similar to the earlier one. We can see here that the 5 translated feet are reflected, and we have a mirror line here in the middle. Here is a real-life example. Next, we have the TVRG, the PMA2, or the spinning sidle. It has a glide reflection with alternating vertical mirrors and 180-degree rotations. This is the visualization. The feet are facing each other in alternating motion. This is supposed to be an inverted letter N. but unfortunately the editing software doesn't offer the inverting letter option. Here is a real-life example. Next, we have the TBHRG, the PMM2, and the spinning jump. We have a vertical mirror symmetry, a horizontal mirror symmetry, and a 180-degree rotation where the mirrors intersect. The intersection here lies in the mirror lines of the horizontal reflection and the vertical reflection here. And afterwards, this is the image being formed. Here's a visualization, a real-life example. Now let's talk about the wallpaper groups. First, let's have a brief historical background using a timeline. First, in the years 1238 to 1492, the Alhambra, or a walled city and fortress in Granada, Spain, was built. It has been believed that the 17 classified wallpaper groups can be found here prior to its discovery. Next, we have M.C. Escher, the founder of the symmetry groups. He is a Dutch graphic artist who became fascinated in the art of symmetric patterns because of the Alhambra. In the 18th century, we have Camille Jordan, Evgraf Stefanovic Fedorov, Arthur Morris Schoenflies, and William Barlow as the main contributors to the classification of crystallographic groups. In the late 1860s, Camille Jordan, a French mathematician, discovered 16 of the 17 wallpaper groups. Later that century, the other main contributors classified the 17 wallpaper groups which are present up until this day. Now let's talk about lattices. Lattices, for any point, the collection of translates of it by translation symmetries of a pattern forms a lattice. For the first type, we have a parallelogram in tabular form. We have a symmetry group of 2, which is notated by the IUC as P2, a notation order of 2, and none for reflection orders. Next, we have a rectangular one. It has a rectangle as a fundamental region. Next, we have the symmetry group here as the number 6, the PMM, notated by the IUC. We have a rotation order similar to the previous one, but here we have a reflection order of 90 degrees. Here is the rhombic one if the fundamental region is a rhombus. We have a 9 symmetry group, rotation order of 2, and reflection order similar to the previous ones. Next, we have a square lattice as the fundamental region. We have a symmetry group of 11, P4M, a rotation order of 4, and a reflection order of 45 degrees. Next, we have a hexagonal one. If it has a 60-degree rhombus as a fundamental region, it is considered as a hexagonal lattice. You can look closely at the details of the table here to see the characteristics. Now let us talk about another naming system used in the International Union of Crystallography notation. Here is a table of the 17 wallpaper groups and their corresponding number of reflections. Next, we have the composition of symbols. We have the letters P and C, which stands for the type of cell the pattern has. We use the letter P for a primitive cell in a region, using only translations. Now we have the letter C as a centered cell for a rhombic lattice that is twice the area of the primitive cell. Next, after the letters P and C, we have a number following it, which is the highest order of rotation for the wallpaper group. Next, we have the letter M for the mirror reflection, the letter G for the glide reflection, and the number 1 if there is no symmetry axis evident perpendicular to an edge of the cell. The last symbol here is a symmetry axis at an angle to an edge of the cell. Here we have an example, the P11. We have a breakdown of symbols here. We use the letter P since this is a primitive cell. We have the number 1 here written since this is a 360-degree rotational order. And the number 1 follows it as well since there is no reflectional symmetry. And lastly, a number 1 as well since there is no reflection or glide refraction in the line. Here is another example. We have the P2MG. We have a breakdown of symbols here. We use the letter P for a primitive cell, the number 2 after for a 180-degree rotation, the letter M for a mirror reflection, and the letter G for a glide reflection line which can be found perpendicular to the x-axis. Now let us discuss the 17 types of wallpaper groups. First, we have the first symmetry group, which is the P1 notated by the IUC. We have a parallelogram for the type of lattice. For this wallpaper group, we have no rotations, no rotational orders, reflection axis, and glide reflections. As this is the simplest type of symmetry group, it consists only of translations. Let us see what this means. We have 5 triangles here. From this line, vertical line of triangles, this is translated 4 times in the plane without changing its orientation. This can also be visualized here using blue lines. This can be visualized as right angles of a triangle or the letter L. Here's a real-life example. We have cubes in the center, which is translated horizontally and vertically. Next, we have on the sides here, we have squares being translated. And we have diagonal translations of triangles. This can be found in Basilica di San Marco in Venice, Italy. For the second symmetry group, we have the P2, we have the IUC notation. For the parallelogram, we have this is the type of lattice. For the rotation, we have the number 2, and the order of rotation is the number 2 as well. This depicts a 180-degree angle rotation. While for the reflections here, we have none. The fundamental region here is half of this type of lattice, which is the parallelogram. Let us visualize here. Looking at the right picture first, we have a red diamond. This depicts a 2-fold center of rotation, which can be applied here. We can see that this is the fixed point of rotation. We can see that this triangle is rotated at a 180-degree angle using a counterclockwise motion in the plane. Here is a real-life example. Now for the third one, we have a symmetry group of 3. We have IUC notation of P3, the naming system used. We have a rectangular type of lattice. We have no rotations and order of rotations, but we have a reflection axis, which is a parallel one. Hence, we can denote that this is the first group that contains reflections, but does not contain glide reflections. The fundamental region here is the rectangular lattice type. We can visualize here a red triangle for the fixed point. This is a 3-fold center of rotation since 3 triangles are being rotated. This can be applied here as well. Since here 3 triangles are rotated, it is rotating around the fixed point. These are also considered fixed points, these 3 triangles, triangle 1, triangle 2, and triangle 3. And for this one, this applies here as well, triangle 1, triangle 2, and triangle 3. And the same goes for all types of the triangles repeated here. Now let us proceed to the fourth symmetry group, which is the P4 notated by the IUC. We have a rectangle for the type of lattice, and we have a glide reflection. But for the rotations and reflection, we have none. This is the first group that contains glide reflections, and the fundamental region here is the rectangular lattice type. Let us take a look at the characteristics first. We have the direction of the glide reflection parallel to one axis of the translation, perpendicular to other translational axis. Let us visualize what this means. Let's have a red diamond as a 2-fold center of rotation symbol, and the square here as a 4-fold center of rotation. We have a 4-fold center of rotation, or the fixed point here, since 4 triangles are being rotated around it. And this can be applied here as well, since these triangles here, triangle 1, 2, 3, and 4, are being rotated outwards around the fixed point. Here's a real-life example. We have the Alhambra pattern in Granada, Spain, which was discussed earlier. We can see here that there are right angles evident, and it is going outwards, both outwards and inwards. Now let us have the fifth symmetry group. We have CM as the IUC notation naming. We have rhombus for the lattice type. For this one, we have no rotations and rotational orders, as well as grand refractions, but we have reflection axes, which are parallel. Here, the fundamental region is half of the rhombus, or the lattice type. Now let us take a look at this. We have new symbols here. For the double lines, this is a symbol of the axis of reflection. This is also known as a mirror line, where the reflection takes place horizontally. And this is the axis of the glide reflection. Here we can see here that these two triangles are reflected horizontally. And this is a glide reflection, since it is moved here and reflected at a 180-degree angle. Here's a real-life example, which can be found in an Alhambra wall pattern as well in Granada, Spain. For the sixth symmetry group, we have the PMM, notated by the IUC naming system. We have the rectangular type of lattice. We have two rotations, two rotational orders, which means this is a 180-degree angle of rotation. Next, we have a reflection axis of 90 degrees and none for the glide reflections. The fundamental region here is a translational group of rectangles. Here is a visualization. The two centerfold here is used using a symbol of a red diamond and the double lines here. This is the mirror lines. Since this reflects, this is being reflected, if you will notice, the triangle 1 and triangle 2. And for this is a vertical mirror line, by the way. And for the horizontal mirror line, we can also see that it is a reflection. And this is the fixed points, since we can see that these triangle 1, 2, 3, and 4, collectively these four rectangles here are being rotated around the fixed points, similar to the other fixed points in the region. And this is applied for all fixed points here. Next, we have the seventh type, which is the PMG. Using the IUC notation naming system, we have a rectangle for the type of lattice as well. Here we have a rotation with an angle of 180 degrees. And yes, we have a reflection axis of parallel. And we have none for the glide reflections. Feel free to pause this video to look at the characteristics, but here I am going to highlight the fundamental region, which is the quarter of a rectangle. We can see here what this means. Let us take a look at the right picture first. These blue lines can be considered as the right angles of these right triangles. We can see here that these are reflections. And we can see here that based on this mirror line, denoted by a double line, we can see that this right triangle is reflected horizontally here. And we can see that in the fixed points here, we can see an angle of rotation here. We can see that this is a rotation here and here. Okay, let us proceed to the next one. We have the 8th symmetry group, which is the PGG according to the IUC notation naming system. We also have a rectangular lattice type. We have two orders of rotation and rotations, which means 180-degree angle, and none for the two types of reflections. In the characteristics, the fundamental region here is the rectangle, a quarter of a rectangle specifically. Here we have a combination of the red diamond and the broken line, since this composes of a rotation and the reflection and the glide reflection. Here we have the fixed point. We can see that these are rotating around the fixed point, these two triangles here. This is a twofold as well, since two triangles are rotating around the fixed point. While for the axis of the glide reflection, we can see here that it is reflected vertically here and horizontally. But in the vertical ones, let us emphasize this. We can see that this right triangle here can be denoted as translating here and then being reflected at a 180-degree angle. Next, we have the 9 symmetry group. We have the CMM, or the IUC notation naming system. We have rhombus for the type of lattice. We have 2 rotations and 2 rotational orders, which means this is a 180 degree as well. And we also have a 90-degree reflection axis. For the fundamental region, we have the quarter of a rhombus. Here, let us take a look at this visualization. We have a combination of red diamonds, broken lines, and double lines, which depicts a 2-centerfold rotation. We have a glide reflection here, and we have an axis of a reflection. If you will base it from this diagram, we can see that these 2 triangles here are rotating around the fixed point here. And it is also being reflected horizontally here and vertically as well, which forms this type of patterns. Next, we have the 10 symmetry group. We have the P4 for the IUC notation naming system. Next, we have the square for the lattice type. We have 4 rotations and 4 rotational orders, which means this is a 90-degree angle of rotation. For the 2 types of reflections, we don't have for those categories. And for the fundamental regions, we have the quarter of a square. Here we can see that there are a combination of 2 centerfold rotations and 4 centerfold rotations, symbolized by a red diamond and a red square. We can see here that the 2 centerfold occurs in the middle, since these 2 triangles here rotate around the fixed point, and these 2 triangles, triangle 1 and triangle 2, rotate around it as well. This is not considered as a group of 4, but considered as a duo. Next, we have the square here, since triangle 1 here, triangle 2, triangle 3, and triangle 4 rotate outwards around this fixed point. And after this composition, we can form this type of pattern. The similar real-life example earlier can be applied here as well. Next, we have the 11th symmetry group, or the P4M for the IUC notation naming system. We have a square lattice type. For the rotation and order of rotation, we have a plus sign here. And for the reflection axis, we have a 45-degree angle for this one, and we have none for the glide reflection. This wallpaper group uses a lattice type fundamental region of a quarter of the square. Let us take a look at this one. It may look complicated, but let me break it down for you. Here is a symbol. We use the 4 symbols which were discussed earlier, and this is a combination of the 4. Let's have first the 2 centerfold rotation. We have this one. This is considered as 2. Here, triangle 1 and triangle 2. Triangle 1 and triangle 2. This is rotating around this fixed point, similar to these triangles here. We have the centerfold rotation here, or centerfold rotation, since these triangles rotate around it. 1, 2, 3, 4, and another group 1, 2, 3, 4. For the axis of reflection, we can see that here there is a diagonal reflection evident in this wallpaper group. And for the axis of reflection, we have diagonal ones as well, running through the fixed points of the 2 centerfold rotations. Hence, we can form these patterns after a combination of these 4 compositions. Here is another example. We have the wall mosaic from Alcázar de los Reyes Cristianos in Cordoba, Spain. For the 12th one, we have the P4G. For the IUC notation, we have a square type of lattice. For the rotations and order of rotations, we have asterisks as their superscripts, and we have a 90-degree angle of reflection. We can see here that this group contains 60-degree rotations, which is the reason for this asterisk here. Okay, let us take a look here of this visualization. This is a little bit similar to the previously discussed one. It has a combination of the four as well, but the four centerfold rotation is in the center, since there are four right triangles rotating around it. And for the fixed notations here, twofold notations, we can see two triangles rotating around it, right triangle specifically. And we can also declare that these angles of reflection here are formed diagonally running through the fixed points of twofold rotations. And we have diagonal ones, but it passes to the four centerfold rotations. Hence, this is the pattern which can be formed repeatedly along the plane. For the 13th symmetry group, we have the P3, or for the IOC notation. We have a hexagonal type of lattice. For the rotations and order of rotations, we have the number 3. The number 3 means that it has a 120-degree rotation. And for the reflections, we have none. Here we have a new symbol, we have a triangle. Since this is a three-centerfold form of rotation, we have the fixed point here, since there are these three triangles here are rotating around it. For these fixed points here, we can see that these triangles, triangle 1, triangle 2, and triangle 3 here. These are the types of rotations around it. And for this one, we have these here, 1, 2, 3. For this one, it's triangle 1, triangle 2, triangle 3, and so on and so forth along the plane. And afterwards, this is the repeated patterns which you could formulate after this composition. Here we have the 14th symmetry group, the P31M. It uses a hexagonal type of lattice as well. And for this one, it uses an asterisk for the three rotation and rotational orders. The three asterisks here depicts a 60-degree angle of rotation. And lastly, for the reflection, we have a 60-degree one. Take a look at this example of a diagram. We can see here that it is a combination of three centerfold rotations here, an axis of reflection here, the double lines here, and an axis of glide reflections. I have used a yellow triangle here to depict the center. Here we can see that these triangles are rotating around the fixed points. We have the two triangles here, two triangles here, two triangles here, two triangles here, and so on and so forth around the plane. And this can also be depicted as a reflection, since this one, it is reflected here, triangle 1, triangle 2, diagonally. It is reflected in a diagonal mat. And after the composition, this is the patterns that can be formulated. For the 16th type of symmetry group, we have the P6 for the IOC notation, we have the hexagon for the type of lattice, and we have 6 rotations and order of rotations. While for the two types of reflections, we have none. The number 6 here depicts a 60-degree rotation as well. Let us take a look here. We have a combination of the red diamond, the triangle, and the hexagon. We can see here that the centerfold rotations here are 2. We can see here triangle 1 and triangle 2 rotating around it. For the triangle 1, we can see these 3. Triangle 1, triangle 2, triangle 3. These 3 are rotating around it. And for the hexagon 1, it is in the center. Since we have 1, 2, 3, 4, 5, 6. 6 right triangles rotating around it. Hence, this is the type of repeating pattern that you will form under this wallpaper group. Here is a real-life example. This wallpaper group is similar to a star. So we can see here that this is the hexagon, the main center point, fixed point. And we have here the triangle ones. Since we have 1, 2, 3 symmetrical objects rotating around it. And for the twofold center of rotation, we have this one and this one. And repeatedly, this forms a mesmerizing effect. For the last wallpaper group, we have the P6M. Under the IOC notation, we have a hexagonal type of lattice as well. We have 60-degree rotations and rotational orders, and we have 30-degree reflectional axis. Here, this is the combination of almost every symbol. Let us take a look here. We can see that this uses the two centerfold rotation here, since these two triangles are rotating around it. This triangle here, since it has three triangles rotating around it. And the axis of reflection here, I have not inputted it here since it would be crowded, it would be hard to depict. So let us take a look here for the basis since it has a similar pattern here. We can see here that the axis of reflection goes diagonally in all ways. And also we have the horizontal axis of reflection. So we can declare that almost every triangle here is reflected for every type of motion. And lastly, we have the 6 centerfold of rotation for the center, since we have 6 sides here. 6 combinations of triangles, forming the hexagonal lattice here. And in return, we have this type of pattern repeating around the plane. We can see here, in an example, we have Basilica di Santa Maria Maggiore, a wall in Rome, Italy. We can see here the hexagon here. We can see we can input a triangle here for the threefold rotations here. We can input a diamond here for the two triangles of the diamond. We can input the 6 hexagonal fold of rotation here in the center. And this uses a hexagonal type of, a diagonal type, of axis of reflections. Now let us take a look at this Wallpaper Groups simulation website. You can type this link here, and we will have an interactive activity. Now let us take a look at this website and how this works. Let us explain here. First, let's have the simplest type of wallpaper group, the P1, which uses only translations. Let us use the color blue, and you can use the line width here. Let us have the fourth one. Let's make it a little bit thicker. And the tool here, we can use different types. Feel free to explore this one. But first, let me form a triangle. Here, we have one. As you can see, these triangles are being repeated across the plane as you draw the lines. And it creates a wallpaper group efficiently and effectively using this digital platform. If you want to see this triangle in different forms of wallpaper groups, let us take a look here. We have the PG. As you can see, it adds another vertical line here of triangles being translated. Here we can see a reflection. The CM1, we have reflections as well. Let's have the P2. Feel free to explore this one. You can use your creativity to create mesmerizing patterns using the art and science of mathematics. Okay, that is all for this video presentation on wallpaper groups, the hidden art of geometry. I hope you appreciate the significance of wallpaper groups in appreciating beauty, aesthetics, and mathematics in nature. Thank you very much for listening. Once again, I am Remus Gem A, Rivera, your lecturer for today.